Also, I want to take a little bit of a different approach today as well. What I was thinking is because there's only very few people today, and we don't have anything exceptionally important to cover because we already kind of like got ahead of the class. Why don't you guys ask any of the questions that you have regarding the content that we covered in the coming week after the midterm too? So that includes probability, sequences, anything from the homeworks or whatever. Like any topic that you randomly want me to focus on today, because we can use the session to our advantage and kind of go over that. So please feel free to talk to me or just put it in the chat. I'll be monitoring both of them, and then we'll begin in like a few minutes. And if you don't have any questions or anything, you can just tell me what do you kind of want me to focus on today, because you guys are here for a reason. And I want to make sure you get what you want.
Well, yeah, we could do some of the probability like questions
Yeah.
that you said.
Uh-huh.
I think I get it, but I might have a question as we do them, and then I can ask as we do
Absolutely.
the
Yeah.
questions,
So
because
we'll
usually that's what happens.
Yeah, probability is what I'm gonna keep a special tab on today. Other than that, if there's anything else um, that was probably missing from the back or something else, yeah.
Yeah, I was kind of I feel like I could use a little bit more practice on probability and like PDFs and like CDFs.
Yeah.
And I was also kind of stuck on the last question of WebWork 10.
Okay.
Um
The
so
Ebbinghaus one, the
I think
differential equation, you mean?
oh no, it was um the one where you have to take a repeating decimal
Oh,
and
okay. So you're already ahead of them. I thought you were talking about
yeah.
the previous web break, but we'll talk about that
Oh,
question in detail
okay.
today too. So we'll
Okay.
get over that one too. All right.
All right, thank
So
you.
probability and that for now. Other than that, did you have any trouble with any of the other questions in the web break? I think they're fairly straightforward in web break 10.
Yeah, I don't think I had too many problems. I don't
Yeah.
remember
Because
there
most of them
actually
are just going to
being.
be like either eyeballing, finding the formula, taking a basic limit, or just using the geometric series formula, right, to kind of find the sum.
Yeah.
So,
Yeah, I don't think they were too complicated.
yeah. I would request you to send me like a picture of your number or like just type in your numbers in the chat so I know when I go over question 10 version of your marks so we can just go over that one, you know.
Okay,
Yeah.
sure.
Just send it over to me, yeah. Hey Oscar, I see you just joined in. Just to update you, I was thinking we're gonna have a different kind of a session today because the Wahlberg is due like on April 10th. So I want to take today to talk more about probability and some of the questions that you might have. So if you have any questions that you want me to go over or any concept that you feel like you need more help with, definitely let me know, talk to me, or put it in the chat, so I can just keep a tab on it. Now with that being said, I think we should start. Should not wait for too long. Okay, so if we start with the first few questions on probability, where I'm gonna give some template here again, where x is gonna be a continuous random variable. We have something we call a PDF associated to it, denoted by small f of x. Then we have a CDF associated with 2, which we call the capital F of x. We know the key relationship is that the derivative of the cumulative density function is going to be your probability function. Or if you want to write it in the other way, you can be like this. Okay, key things to keep in mind. Of a data's value. And this sums up the likelihood. So we know the purpose of these two functions are as follows. We know a bunch of information here too. So if I was to kind of like go over the notes and consider their example, they said, let's say you have you know, a probability that you take a bus, okay? From home, and we know the bus arrives every 20 minutes. Okay, so if you know a bus arrives every 20 minutes, then when you get to the stop, you will have to wait X minutes, right? So now, because depending upon whenever you leave the house is, you know, random, it's probably, you know, sometimes a little bit different, a little bit different on other days. So the probability of you getting different times is going to be different. Okay, on average you'll be like in a certain region, but most of the time the waiting time X would range between minimum 0, maximum 20, right? So it could be situations where you leave house and you reach a stop, and right away the moment you hit the stop, you have a bus waiting for you, so you didn't have to wait any time. So that's why 0 minutes of waiting time. Or sometimes, you know, you probably just reach the stop and the bus just left, so we'd have to wait another 20 minutes to get the other bus, right? So you can have this X kind of be randomly taking values depending upon randomly leaving the home and getting into those situations, right? So when you're given this this idea, how would you describe the probability for this kind of thing, right? So what is the chance of you, let's say, waiting in between, you know, let's say 15 minutes or 18 minutes, right? So what is the chances of you waiting like 15 to 18 minutes, right? So if you think about it this way, then you know that this particular you know, idea would mean that, okay, there's a possibility for you to be able to wait 15 minutes. How many choices do you think you have in between the range of 15 to 18? Remember, 15 to 18 minutes is a time value, right? So how many possible minutes are there, or like any data points are there between 15 to 18? 2, 3, infinite? What do you guys think? 4. So you have 15, 16, 17, 18, so that's 4, yeah. And that's a minute value. Is 15 minute 30 seconds also a valid data point in this zone? Yeah. Infinite is the correct answer though. Because there's so much time there, right, in between that possibility, that you can just kind of be like, you know, there's so many possibilities to choose from, right? So when you see, when you want to pick like an equal likely probability for this kind of situation, what is the probability for you? So probability of X being equals to exactly 15 minutes. Think about it this way. So out of, given that you have infinitely many choices of times between 0 to 20, what is the probability of you getting to wait exactly 15 minutes for the bus? The key thing to remember, there's infinite possibilities of time. Close to 0, yes, and it is in fact 0 in this case. Because of the description or the behavior of a density function, the probability of the random variable taking one precise exact value is 0. Okay. However, you can describe the probability being between these two numbers, right? And this is basically going to be the integral from 15 to 18 of the PDF that's associated with this whole system. Okay. Does that thought kind of make sense? Like how do you add up probabilities, right? It has to be a range. A random variable x needs to be in a range. It cannot be in just like, a fixed a value, because that way you will have infinite possibilities, and it would not make sense for this to be exactly precisely equal to that number. Okay, so now I'm going to show you a probability density function for this kind of case. It could be a fairly standard one, and I'll show you what it means. Okay, so if I choose f of x to be 1 over 20, where x, goes with a domain of 0 to 20. Even though the function is not dependent upon x, you can kind of see what's happening here, right? That's just the whole idea. Now, we got to have a checklist. For f of x to be a PDF. So any function cannot just be a PDF. We have to be very careful for it to be a PDF, okay? So the first thing you want to check is the f of x is always positive for x. Okay, that's the number one criteria. Do you think that passes number one criteria? Yes. So number one criteria is check for this. The other criteria that you should have here is the integral of f of x dx from a to b, where a to b are the bounds of x. Okay, x could be from a to b, in this case from 0 to 20, or in other cases from negative infinity to positive infinity. It could be anything, but as long as you're taking the integral f of x over the whole possibilities of x values, this should always be equals to 1. So we still have to check it. Does that function obey this or not? Let's check it. So to find the second criteria, you would want to take the integral from 0 to 20 of 1 over 20 dx. This will be x over 20 from 0 to 20, and there will be 20 over 20 minus 0 over 20, which is 1. Right? So now, because it passes both the checklist marks, this is a valid PDF function. Okay? So now I have this, this is my valid PDF function, and this would be able to describe the function's value in the whole behavior of the probability distribution that we just gave. Any questions about checking the checklist for f of x to be a PDF? This is very crucial stuff. Okay, not any function could be a PDF, and for a function to be a PDF, it must obey two properties. First of all, it should be positive for all values of x. Second of all, it should be having an integral of 1 over the interested domain. If everybody's good, let me know. We can move on. Okay, good. Let's go. So now that we have a PDF, we can go back to our original question. How do we find this quantity, right? How do we find the probability of x being in between 15 to 18? Then we can just take the integral of this from 15 to 18 of 1 over 20 dx, right? So that way what I'll get is, I'm going to be able to get x over 20 from 18 to 15. That will be 18 over 20 minus 15 over 20, which happens to be just 3 over 20, right? And if you want to convert that into percentage, you'll be able to find a number. I'm not going to do that. It's just too much work. I guess this should be like around 0.15, I guess, if I'm not mistaken. But yeah, you guys can do that too, not too bad. So 0.15 is the probability here, which means there's a 15% chance that you might have to wait 15 to 18 minutes. Okay. And all of these numbers are because of this particular chosen value of f of x, right? Of course, if you follow a trend that you always leave like at 7:05 and the bus that you catch is always at 7:15, so you're most likely to wait 10 minutes, right? So that way you'll be like, okay, that is the regular trend, and that's probably what happens in natural life too. When you go out there, you always have like a certain fixed time that you leave, and you catch this particular time bus, right? So it's not gonna be like equally likely and equally like, in that sense. In that context, for you to wait 15 minutes, you would probably have to be like really late, Because if you usually wait for 10 minutes and then you would have to wait 15 or 18, that means you're going to miss that bus, right? So all of these distributions and those scenarios or those ideas depend upon this function. We came up with this very basic function that the likelihood of each event happening is equally likely, so 1 over 20. That's why you see this. But in other cases, it would not be this case, usually. Okay? So now if I want to ask you a different question, right? If I want to ask you, let's say, what's the probability that your wait time is up to 15 minutes and not more than that? Let's say you want to find this. Okay? How would you want to find the probability of this happening? Bounds 0 to 15? Yes, exactly. So then you have a 0 to 15 integral of the f of x function. Right? Exactly. So you guys are right. Integral from 0 to 15 is what's going to get you the answer. And now everybody knows why we're going to choose 0, because that's where the thing starts. You can have a minimum wait time of 0 minutes, and all the way up to 15 is you're going to add up all the probabilities at that point. And this will be a significant number. You know that's going to be 15 over 20, so which is like 75%. Right? So there's a 75% chance that you might have to wait between up to 15 minutes. And that's okay. That's possible too. But how about I ask you, what's the probability of me waiting less than, a given amount, which I'm going to call this capital B. Then you guys can see the dynamic is going to be very similar. All you would do is you're going to have 0 to this B of f of x dx. And that would just be equals to B over 20, right? Only because of the nature of the question, because we had a constant function. So if you do the integral, you would get B over 20. Does everybody agree that we're going to get B over 20? Right? So this particular question will have this behavior, but we want to have some function that helps with the accumulation of probabilities. Okay? Right now we were cool looking for in between some region, that's fine. But if I want to do this idea that I want to see what are the odds of me waiting up to this point, then I should have some cumulative function there too. So that's why we use cumulative density functions. Okay? And a cumulative density function of CDF is described as this. So CDF, as per the relationship, is the integral of PDF, right? And this bound A is the starting of the data. Okay, so X can be starting from this point, and this would need to go to some capital X on top. So you can just, it's just notationally different to kind of tell you that this X is denoting something, where this is the point up to which you need probability. Okay, so if you want to find, I'm going to denote these things with capital F of x. This will be small f of x, right? So if you want to find probability, let's say, being less than 15, right? In the case where x goes from 0 to 20, if you know this, that could be calculated by taking the integral from 0 to 15, as you guys said, off the small f of x dx. Or that could be computed by just one single operation by plugging in 15 in the place of capital F. Because the purpose of a cumulative density function is to add up all the probabilities up to the point we're looking at. In this case, we can interpret both of these results in this fashion. Does this make sense to you? Like how cumulative density function is useful? And I'm just going to solve it too, to just make sure that we kind of like naturally have this extension. So let's find the CDF for this, right? So capital F of x will just be the integral from 0 to some x of 1 over 20. Right? And when you do that, you get And then once you do that, we get this result to be this way. You see the capital f of x. It's very hard to switch colors. My brain just kind of stops working. In the middle is your. So now I found my capital f of x, and I had a question says, it is that symbolic is true only if your lower bound is 0. Yes, because whenever we ask this kind of probability, which specifies just like one side, we just want it below this or above this or somewhat in that sense, then we can use that idea. And in this case, it's a 0, it's fine. But in any of the cases when they go like find the probabilities of 15 or below, well then the below is just like wherever you start. In this case, you start at 0, so that's why you're going to use 0. But if you would have started at some other number, you would just go back to that number too. Okay, so now we have a CDF function. And we already said to find that value, we just have to have 15 over there, or like, whatever number we want to find. So, probability of x being less than 15 is capital F of 15. And hence, it's just going to be 15 over 20. Which is 75%. This is exactly what we got in the previous example. Right? So your approach of setting it up from 0 to 15 was good too. But it'll be nice if you just have like one function that spits out the numbers for you. Right? And that function is the CDF function. So now you should be able to understand that there are two functions associated with everything, and their importance and their significance too. Can it make sense? So now I'm going to show you like a bunch of questions that are typically being asked on the exams and stuff. If there's any question about this, please feel free to ask me right now, or else we can just move on.
So would this still work? I know you said that the 0 would just be any of the starting points. So let's say like it was just 1. Would it then be like f of 15 minus f of 1?
Yes, because then you would have a starting point at 1. It would not change anything, because when I ask you this question here, you would be like, what's the possibility of x being less than 15? Kind of translates to what are the possibilities x between 1 to 15, isn't it? Because 1 is where you start. Right? So if any values of x below 15, x starts at 1, so it kind of like hypothetically means you're only going to stay between 1 and 15, right?
Yeah.
So that's why your integral will always be in that fashion too. And now we have a more robust example. We're going to do that, and then we'll discuss in detail what's going on, okay?
Okay, thank you.
Let's go over this one. So we have x as a random variable. And they want us that we have a density function too. We have a PDF associated with that, given to us as small f of x equals to 2x plus 1 to the power of minus 3. Okay? And it's defined for x values bigger than 0. So now, just to make sure the context is clear, x is a random function, a random variable, right? It has a density function. And x can be only positive values, 0 or positive, right? So now in this case, the starting point is 0, the ending point or the end possibility of x being is infinite because there's no bound on top of it, right? Does that make sense to everybody? Part A is to verify if f of x is a PDF. And the checklist tells you have to check whether it's going to be always positive for the values of x in the domain, or its integral should be equals to 1, right? Both the things should be match up. So let's check. So when you check number 1, because f of x could be written as 2 over x plus 1 cubed, right? If you're given this way, this function is always going to be positive for x greater than 0. Can you see why? Does anybody have any questions of why this won't be the case? It's a fairly obvious thing. If your x is positive, then x plus 1 is going to be positive, and cube of a positive is positive, and hence whole thing is going to be positive, right? So you can logically reason why this is going to be positive. So it passes the first test. The second test is to check whether the integral of this over the interested domain is equals to 1 or not. So we're going to take the integral from 0 to infinite here. And 2 over x plus 1 whole cube dx. You know, this is going to be an improper integral, right? Because of the bounds being infinity. So let's turn back to our notation and be like limit b approaching infinity, integral from 0 to b of 2 over x plus 1 cube. Now I'm going to do this something special, okay? I'm just going to jump up to the answer. And I want you guys to be able to figure out the how I did it, okay? And that's where the whole important part is, okay? So let's see. This is going to be limit b approaching infinity. This will be negative 2 over 2 x plus 1 whole squared. Evaluated from 0 to b. So the integral, I wrote this integral, the integral of 2 over x plus 1 cube would just be negative 1 over x plus 1 whole squared. Now's the time where you guys will probably have to scratch some of your heads to kind of get this. Chain rule, yes. Chain rule, that's exactly what I did. But it becomes a little bit interesting too, because if you have, you know, I'm going to give you this rule too, just so that because we're on the same page. Whenever you have 1 over x to the n, right, in an integral, you can turn this into integral of x to the power of negative n. And when you do the integration process, you'll be left with x to the power of negative n plus 1 over negative n plus 1. Right? So whenever you do this, and this could be converted into this. Right? So you can pretend, in this case, you would have 2 outside. You have 1 over x plus 1 whole cube. Right? So all you got to do is have a minus n plus 1 here, which means a negative 2, right? Because minus 3, this will be a minus 3 plus 1 of the rule. And you'll have the x raised to the same power 2. So it'll be, sorry, this needs to be changed back to n plus n minus 1. Because when this comes down, you have to negate the whole thing, right? So when that comes down, you get this, and x to the power n minus 1, which means you have to reduce the power from 3 to 2. So because this is a chain rule problem, we'll have x plus 1 instead of this. And of course, you have to divide by the derivative of the inside part, which happens to be just 1, so we don't really care. So that way you will have the integral shaped up like this, which looks like negative 1 over 2 times x plus 1 whole squared. And because of this extra 2 out there, they cancel each other out. And that's how you get this result. Okay. And there's no problem if you aren't that fast at doing things. You can still go by the approach of chain rule. Or you can go by the approach of the u substitution, right? If you would want to integrate this, you would substitute x plus 1 as u. And that way it will become a little bit easier of an expression to integrate. But other than that, it's just practice, you know. The only reason why I was able to get that there fast is because of just a lot of practice. But other than that, does it make sense to everybody? Like how this integral works. And getting good at integration is like a side job here, because we're now applying integrals. So we don't really need to teach how to do integrals here. And it's just depending upon the person. They can do it fast, they can do it slow, whatever they like. Everybody's good? Move on? Okay, awesome. So this is out of the picture. I'm going to get rid of this so I have space. Now my integral looks like this. This negative 2 and 2 cancels out, so I'm taking limit b approaching infinite of negative 1 over x plus 1 whole squared from 0 to b. This evaluates to limit b approaching infinite of negative 1 over b plus 1 whole squared minus of negative 1 over 0 plus 1, so this 1. Which just evaluates to the limit b to the infinity of basically 1 minus 1 over b plus 1 whole squared. And because b is going to go to infinity, this is going to go to 0. Right? Hence, this answer is going to be 1. Does everybody see how the answer is 1? This is like the longest notational way of solving the thing. You know, you don't really have to do this to like stick to the actual notation and stuff. I just did it because it's a good refresher on improper integrals. So now I passed the second test too. So hence it is a valid PDF. That's how you would get the first question on the exam usually, where they would ask you to find this whole idea. Okay? Any questions about this part? Cool, we're going to go to the next one. Now, when they want you to do this, I'm going to write the f of x here again so that we can have it handy. That's the function given to us. The given domain is x greater than or equals 0. They want us to find the part B of the question is find the CDF. And you know by formula, the function CDF capital X is just the integral of the PDF from the starting point, which in this case will be 0, till some random x that we choose. Right? Now this definition should be crystal clear. Now all you have to do is solve this integral. Right? And now let's do that. We know this will mean that we have to evaluate negative 1 over x plus 1 whole squared from 0 to some x. Now you guys know why the integral is just that. Oh, it should be negative. My bad. Negative 1 over x plus 1 whole squared. And then when you plug in the bounds, what do you get? You would get negative 1 over x plus 1 whole squared minus negative 1 over 1 squared. Right? Essentially leaving you with 1 minus 1 over as your cumulative density function. How does that feel? Solving for cumulative density function given a probability density function. Any questions regarding this process? Okay, everything's good. Awesome, we're moving ahead of this. So now, after we're done this PDF and CDF, let's try to put them to good use, right? I'm going to have these weird interpretations of this. So I'm going to put both of these functions down on the next page. It was 2 over x plus 1 whole cube. And the cumulative density function was 1 minus 1 over x plus 1 whole square, right? Yeah, that was it. So now we have both of these functions. How would you want to answer this? C part will have to compute probability this. You all should be able to kind of find that this is disgusting, and they've written it in this form is kind of very weird. So I would rewrite this in a more natural way, how we usually think. Right? The question just kind of tells you the same thing, but now it's written in a more nice way. So how would you like to find this quantity? Would you want to use a PDF or a CDF? Anybody? So CDF at x equals to 2 is going to give you all the probability sum up to 2. Right? But do you want that? You want it only from 1 to 2. Right? So you're going to get 0 to 2 because x starts at 0, remember? So if you do capital F of 2, that tells you the sum of all from 0 to 2, which is cool. Okay, so now you change your answer to PDF with 1 to 2. That's good. Let me just give you another way of looking at things. So before we go there, does everybody agree PDF with bounds 1 to 2 would always work, right? So there's a short way. You'll just be like, okay, 1 to 2 of 2 over x plus 1 whole cube dx and call it a day, right? Does everybody agree that works? To find the answer, yes? I'm going to give you a more intriguing way of looking at things in that fashion, right? So f of 2 is going to give you sum of all from 0 to 2. What about f of 1? F of 1 is going to give you sum of all from 0 to 1. And to get sum of all from 1 to 2, can't you just subtract them? Could also be written as f of 2, f of 1. Right? Because if you're looking for the probabilities, the sum of all the probability of possibilities from 1 to 2, you can take the sum from 0 to 2 and subtract 0 to 1 from it to get the 1 to 2. Isn't it? Right? So this is where you would have a complete flexibility of choosing whichever thing you like. You know both the cases are going to work. So the cumulative density function has already done the integral, so you don't really have to do it again, right? This integral, you don't have to do it again. That's why to find the probability, all you got to do is just plug in these values and find it right away. Okay, so if I was to compute it using this approach, all I have to do is plug in 2 into the function, so 1 minus 1 over 2 plus 1, which is 3, so 9. That's the f of 2 value. And then f of 1, we're plugging in 1, you have 1 minus 1 over 4. So this would give you 1 minus 1 minus 1 over 9 plus 1 over 4. So the answer is going to be 4, basically 9 minus 4 divided by 9 times 4, that's 36. So that turns out to be 5 over 36. And you can cross-check this answer too with taking the integral, and you'll be getting the same result anyways. Okay? So how cool was that to just use CDF in that fashion? So that's good. Another question that I wanted to put up there, the other part of C would want you to solve for this. So I'm gonna copy paste all of this because we're gonna need them in the next page too. Right. And the part C is asking for now this. What is the probability of x being bigger than 3? Think about it for a second. And tell me, how would you solve this? You got both the options there for you. You can choose a PDF or you want to choose a CDF, depending upon how you want to do this. So if you do a CDF at x equals to 3, it tells you the sum from starting up to 3. But what are you searching for? Is it exactly the same as that? I'm looking for probability of x being bigger than 3, right? So yeah, so I have one possibility, which is good, which you might want to do is a PDF from 3 to infinity of 2 over x plus 1 whole cube, right? Yeah, so that's one possibility to find from 3 to infinity. And everybody agrees this is always the case. That's okay. But because we have a CDF, I wanted to put this idea too. So now you want to find the probability of x less than 3 that is just literally f of 3, right? Everybody agrees on that? If you want to find that, So that's exactly what I had this very, very important thing there. So somebody in the chat said, if you do the CDF at infinite, okay? So if you want to do CDF probability of x being less than infinity, is that what you mean, right? And then f of infinity. That's the CDF infinity. Well, isn't that value 1? Well, probability of x being less than infinity is always going to be 1, right? Because whatever that x is, it's going to be smaller than infinity, right? We can be dead certain of that. And as a matter of fact, we did that calculation before too. When we did the calculation here for taking the integral from 0 to infinity, we effectively just computed the CDF at infinity, isn't it? And it's the inherent nature that the cumulative density at the very end of the domain, which means here in infinite, the CDF value at the very end is always going to be 1, because that means you've already accumulated or added up all the possibilities, and because it's probability, sum of all probabilities needs to be equals to 1. Right? So does it make sense? The CDF at infinite is 1. Right? Or like CDF at any endpoint of the interval for a question is always going to be 1. Right? So that way you can interpret this like this. So probability, I can show you this idea of kind of like interpreting this. So probability of x being less than 3 plus the probability of x being greater than 3 should be 1. How do you guys feel about the statement that I just said? Makes sense, right? Probability of x being less than 3 or bigger than 3 is 1, because x would be either less than 3 or bigger than 3, right? So all the possibilities are just going to be adding up in that sense. So now this right here is your f of 3. And this right here is what you're looking for. So all you have to do is do 1 minus f of 3 in order to get this computation right here. Okay? And to answer that question, it will be 1 minus, when you use f of 3, you would get 1 minus 1 over 3 plus 1, which is 16 whole square, which happens to be just 1 over 16. That's the answer. Okay? How do you guys feel about this whole problem? You know, extensively trying to use the concept to find PDF, find CDF, and then how to use them too. Does it make sense? Okay. The reason why you feel the hardest part is the integral in these particular questions is because I would say there's an amalgamation. So like if you have soup, you know, and then you would have like soup with a lot of stuff going on, you would not be able to you know, enjoy the ingredients of the particular thing when there's so much messed up here. Because of the concept of probability being engrossed inside with integrals, it kind of becomes hard to differentiate between what's going on in each of these respective points. So doing integral is a completely different thing. You know, it's just good practice. You can practice on these things. If I would have shown you this integral without the context of probability around it, I'm pretty sure you'll be able to do it. Okay, but because this is like a part of the dish, then it might not be, you know, the perfect time to try it out. So that's kind of like how I would interpret a little bit difficulty with the integral. Otherwise, I don't see any problem with it. Okay, so now we have another quantity that we have to define. So this is PDF CDF. It's out of the way. It's done. Now we have a formula that if you have x as a random variable, you know its PDF is f of x. Okay, and x is defined for some, let's say, some interval a to b. It could be defined from negative infinity to positive infinity too, but we're going to say for this, it's going to be defined from a to b, some random values. Then the expected value, or in other words, the average value of x, can be figured out by this. The expression is e to the x, or like capital EX, not e to the x. And that integral is just basically adding up from a to b of x times the f of x dx. That's a very fundamental formula, okay, for this. So now let's say I give you a function here. Example, let's do an example. X be the lifetime of a bulb in hours. Okay? So when I give you the context here, can you tell me what x should range from to what value? So what does it make sense for this value to be, you know? Like a lifetime of a bulb can be from what values to what values? Yes, so we don't know 0 to 100. Maybe, yeah, that's a very valid thing, you know? You'll be surprised that bulbs usually last thousands of years, thousands of hours, so we're not going to go there. We're going to assume that a bulb can last eternity, okay? Because we have an example of the longest lit bulb, continuously lit bulb, that has been there for like about 100 years now. So how many hours that is insane, right? So for safety of this argument, I'll just say x can go from 0 all the way to infinity. Okay, because the lifetime could be infinity. We haven't really been able to convince ourselves that the bulb will definitely die before this, right? So does it make sense for choosing the x value to be 0 to infinity? Because we don't know how long it lasts, we're just going to choose infinity. Because theoretically, it can just keep on, you know, going for however. And then we know that its density function, okay, probability density function is given to us as this. They've given us a special function here, which is f of x equals to k e to the power negative kx. Okay. This is like only in terms of k, where k is a constant. Cool. Now what they want us to find, though, is we want to find the average life of the bulb. So when they say average life of a bulb, that means you want to make sure you want to find the average value of x. So a good question there. Will you ever be, you know, asked to find out what the PDF is without being the CDF or anything? Nope. You cannot come up with a PDF just like that. We were able to come up with a PDF in an equally likely case, but usually what happens is PDFs are given or CDFs are given because they're kind of skewed in a sense. They're not the ideal cases. However, you can definitely be asked to check whether a function is a PDF or not, and you know how to do that. Okay? So no worries about it. In this case, they've told us that this is a PDF function, so we're going to assume that they're, you know, once in a while talking truth. So we'll just assume this is a function, and we're going to just keep on working on our way to solve this. Okay? So this is what it is. What I'm looking for is expected value of the lifetime, which means I'm looking for x, right? We have a very straightforward formula to get us with this, and the formula is just taking the integral from 0 to infinity of x times the PDF function, right? So I'm going to do that right now. So expected value of x is going to be from 0 to infinite of x times k e to the negative kx dx. Okay? Does everybody agree this is how we're going to set it up? No conceptual hurdle there. You know, there's nothing crazy. We're just looking for expected value of x because x is the lifetime. Hence, we're just going to have x times that. No trouble at all. Now, because you mentioned that integrals usually a little bit harder in this context, I'm going to detach these contexts first. So let's say I'm going to come back here in just a second. Okay, we're going to look at this integral without the fuss. Let's see, I just had this integral. If I was to ask you to integrate this, k okay, if I give you this integral like that, you can move the k outside because k doesn't really matter here because it's a constant. How would you go about integrating this function where you have x times e to the power negative kx? Do you want to do u sub and then by parts? That's also a possibility. Very well. But what would you want to u sub though? Yeah, so that's one possibility. Let's branch it off. So you'll want to say u equals to negative kx. So du equals to negative k dx, right? So if I introduce that thing over there, your integral will look like what? So because of here, you want to isolate for x, right? Because you have to substitute for x too. So you would isolate that x is equals to u divided by minus k. So the integral is u divided by minus k with a k outside. From there, you will be dx is just equals to du by negative k, right? So you have e to the power u times du by negative k, right? So this k, that k cancels out, this negative, that negative cancels out, so you'll have this expression as 1 over k u e to the power u du. That's a valid way of going there, right? Is that what you wanted to do? Okay, good. Now you want to do by parts, right? So as per the rule of by parts, we want to make sure that we choose the right functions there. So you might want to choose your u as u. Of course, it's going to become confusing. But and your dv as e to the power u, right? And then you find your du to be just du. That's it. That's going to be like a horrible example, but yeah. Du. And then your dv will give you a v as e to the power of u. So when you write this integral, it'll be 1 over k. If you forgot, it's going to be uv minus v du's integral. So that way you will have 1 over k uv, which is going to be u e to the power u minus e to the power u, the integral with du. Okay. So that way your expression is going to be 1 over k u e to the power u and minus e to the power u, and this is just going to be e to the power u divided by k with a u minus 1. And now because u is minus kx, you have to plug it back in. E to the power negative kx divided by k. Because it's minus kx, so I'll always be like, okay, minus kx minus 1. How does this integral feel? On a difficulty level of 1 to 5, where 1 represents easy peasy, 5 represents extremely hard, how would you rate this from 1 to 5? So 2, 4, 2, right? Not too bad. So I would want to discuss a little bit more why you feel 4 is a little bit thing. So we'll talk back after the class, okay? I'll just kind of like go over why do you feel it's a little bit harder in sense, because there's something missing there, right? This should be easy. But we'll talk about it. Don't worry about it. Now, once we have the integral, now we got to go back to the question, right? The question was asking us this, the expected value from 0 to infinite. So we've integrated the function. We know what its antiderivative looks like. So all we have to do is now evaluate this from 0 to infinity, right? So I'm going to be a complete uncultured mathematician and just do it without using the notation of improper integrals. So I'm going to have e to the power negative kx divided by k with a negative kx minus 1 evaluated from 0 to infinite. Okay, so here when you plug in this, you would have 1 over k. I'm going to intentionally write it like this, okay, to make you see that. When this will be negative infinity times negative infinity minus e to the power of negative infinity divided by k. That's the expanded form when you plug in the first expression. Minus when you plug in the 0, you'll have e to the power of 0 divided by k, 0 minus 1. Okay, so I expanded this into first negative kx over k times negative kx, right? So you can kind of see that these k's will cancel out, but I don't really care about that. And then minus e to the power negative kx divided by k. So when you have this expanded form and you plug it as infinity, that's what's going to go. So why I call myself an uncultured mathematician is because I'm just going to say that this, when e to the power negative infinity times negative infinity, is going to be 0. How many of you guys agree with me on this? That this limit is going to be, or like whatever this is going to be, is going to be 0. And it's completely okay if you don't see it, because I haven't shown you. But I just want to test if your natural gut feeling will tell you how it goes. Then I'm going to go with one explanation, which is just going to be intuitive explanation. And then we're going to go hardcore math on this, right? So you agree because you've seen the graph, and that's the whole point, right? As long as you convince yourself, it's all good. No problem at all. You're there. How about you, Oscar? Do you feel it? Clicking in that y is it going to be 0? If not, then we're going to go over that. Yeah, so you kind of have the idea because of e. What happens is you're having two functions here, which is e to the power of negative kx versus the function kx. Okay? Now, as x goes to infinity, e to the power negative kx goes to 0, while kx goes to infinity. Right? So we have this kind of like a race happening between these two functions, exponential function and the regular polynomial function, right? So which one do you think is going to win the race? Depending upon how they behave, right? You know, exponential functions are much faster than polynomials, right? Because they grow and decay so much faster than the regular polynomial. Isn't it? So when you're having a race between an exponential and a polynomial, the exponential is going to dominate. It's going to dictate what's going to happen, right? So that's very important to see here. And this is why you would say e to the power negative infinity times infinity would be 0, because this guy will hit 0 way before this guy hits infinity, hence shutting everything down to 0. How is that? How do you feel about this intuitive explanation? Does it become brings in more clarity on the topic? And if not, if you're not convinced, then we have to go to the L'Hopital's way. You know, like formalize the limit, take the limit, and then kind of like work our way through the whole example too. But I would say it's just not necessary in this context. So we can stick with this. But I will show you, just for the sake of, you know, being convinced with math, I will show you. So we're evaluating this. We have 1 over k. This expression, right, is what we have to focus on. So that expression just simplifies to be e to the power negative kx times k times x. And this, when you take the limit of x approaching infinity, okay, this turns out to be 0 times infinity form. So we know we got to use L'Hopital's rule, so we'll convert this and write it like this. Limit x approaching infinity of x divided by e to the kx. Right, because we had negative kx, we can write this as with a kx in the denominator. Now this becomes infinity over infinity form, which is ready for L'Hopital's rule. Okay, so you have to make sure we apply that rule. So L'Hopital rule tells you can take the derivative of the top and derivative of the bottom, respectively, then take the ratio of them, and then take the limit. Try again. So let's do that. Limit x approaching infinity. The derivative of the top is going to be 1. The derivative of the bottom is going to be k e to the kx. Now when you take the limit, you'll see this becomes 1 over infinity, which is 0. So a mathematical way of proving this using L'Hopital's is this way. Okay? So up to you, however you want to convince yourself. I just wanted to take some time to go over in detail that this could be possibility sometimes too. And, you know, math works in all the sense. How does everybody feel about the L'Hopital's way? Like actually formalizing the limit and solving it. Makes sense, right? Hopefully nobody got confused because of this extra work. So that way you know this is going to go to 0. However, this is going to go to 0 as well because e to the negative infinity is going to go to 0. So you'll be left with this. You'll be having negative 1 over k with a negative 1, which is just 1 over k. So the answer to the expected value problem is the lifetime needs to be 1 over k. Okay, and this was of course in terms of some constant random numbers, but it shouldn't be that big of a deal. You guys understand that, right? So this is how we solve an expected value problem, where you want to see and solve for the value of the thing, right? Okay, so now we're gonna do one problem to just finish it off and call this a day for probability after this point. Okay, so the problem is as follows. So we know that in a lake, you catch fish. Okay, and the mass is random of the fish, or like you used to say weight is better because you only measure weight. Weight of the fish is random, and it also has this probability density function that looks like this. If that's the case, and it's 0 otherwise. So we're given this function. We have to do these steps. So I want to give you guys a shot. So find k. That's the first question. Part B asks you, what is the probability of the fish that you catch is larger than 5 kgs? So you're going to have probability of x being bigger than 5. That's one of the other cases. And the last part is asking you to calculate the average weight of the fish that you catch in the lake. So, average weight. So before we begin this, which part makes the least sense, to find A, B, or C? Like you have no clue about how to do that part, in that sense. So I have one C, and so C is the one that you have no clue. Which part makes the most sense, which is the easiest to find? B, right? Now everybody agrees, and then of course A is also there too. So you kind of have this idea that finding A and B are okay. Finding the average weight is kind of like weird, right? But remember, if X represents weight, then finding average weight is just finding the expected value of X. Isn't it? Right? So now that I gave you a little piece, does it make a little bit more sense of how to do part C, right? It's just going to be another integral. We'll have an extra X multiply with the whole situation, right? Not bad. Not bad at all. So let's start by doing and finding the value of k and see what's happening here. So when you do part A, to find k, we must make sure that if it is a PDF, it should obey the property that is integral should be 1, right? Here we have a function that's defined virtually for anything, because you can example, expect the x to go from minus infinity to infinity. You can have a large gigantic fish, or you can have a very infinitesimally tiny fish in that sense too, right? That is like the context in other ways. But then negative weight does not make sense, so you want to improve this thing to be like, okay, it should range from 0 to infinity, right? So that's like another enhancement that you did. 0 to infinity makes more sense because that's what weight is. Weight could be very tiny, almost nothing. And the reason is why I say almost nothing tells you that it cannot be 0 either. There's nothing in this world which has 0 weight, okay? And if anything has 0 weight, then it doesn't exist. So you want to correct this too. So this will be an open bracket now. The possibility of x could be, open bracket 0 all the way to infinity. Make sense? Right? So now we have this possibility amongst us. That's amazing. We can figure it out of how we're going to see. Now they've bounded the restriction on the function. technically x could be any value, but we know it's unrealistic for a fish to be more than 0 to 10 kgs. The probability for us to find anything below 0 or above 10 is 0. Does it make sense why the probability density function is 0 otherwise? Right? Because having a fish more than 10 kgs or whatever units of weight they're using in that lake is just not possible, right? Does it kind of convey the idea that this PDF is specific for this particular lake in this situation, right? So they've defined it this way. So to find k, we're only going to be interested in integrating over this domain. So the integral from 0 to 10 of k times 10 minus x squared must be equals to 1. That tells me the integral of this function is the chain rule will be this, right? And this needs to be evaluated from 0 to 10 and must be equals to 1. That implies minus must be equals to 1. This is 0 because 10 minus 10 will give you a 0. And here you'll have an expression that k needs to be equals to 3 divided by 10 cube. Does everybody see how I got the k value to be 3 divided by 10 cube? So the divide by 1 came from the chain rule. Remember, when we're doing a chain rule of integration, we want to divide by what you treated as the linear, right? So we have to divide by the derivative of the 10 minus x term, and the derivative of 10 minus x is going to be minus 1. That's why you divide it by this. Okay? It's because of chain rule of integration. If you don't follow this along, you can go back to using USub and it will still work out the same way. Okay? Right now, I will recommend just try to do integrals in the most familiar territory, usually where you are most familiar with. Just do those methods and then slowly enhance as you go. Okay, so I found the k value. We got it. It's very, very easy, right? No problem at all. Now let's look at part B, which you said the easiest. Okay, so finding the probability of it being bigger than 5 would just mean you want to integrate from 5 to infinite, which it doesn't make sense because it's 0 otherwise. So it only makes sense to integrate 5 to 10. Make sense? Why am I choosing the top bound as 10? Because anything above that is going to be 0, so there's no point of even going there. So here I would have k 10 minus x whole squared dx. When you integrate that, same idea. You'll have negative k by 3 10 minus x whole cube evaluating from 5 to 10. That will be negative k by 3 10 minus 10, which will give you 0, and then minus k divided by 3 10 minus 5 will give you a 5, so it will be 5 cubed here. So this turns out to be 5 cubed by 3 times k, and now you're plugging the value of k. That will be 5 cubed divided by 3 times 3 divided by 10 cubed. They cancel out. The value will be 5 cubed by 10 cubed. Okay? So part B is okay? Everybody's cool with that? Shall we move on? Awesome. So we can move on to the next one. The last one is the average weight. So now all I have to do is just integrate the same thing from 0 to 10, but with an extra x in there. Okay? The formula for expected value of x is from a to b, x times f of x. So for me, expected value of x will be from 0 to 10 of x times k times 10 minus x whole square. Right? So before we integrate this, I would just recommend you try to simplify the expression inside a little bit first, because it will save you trouble. So if you do have 10 minus x whole squared. Then it will be x times 100 plus x squared minus 20x. And that comes out to be 100x plus an x cube minus 20x squared. Okay, that's the simplification of what's going to be inside. So this integral could be written as k, chills outside, 0 to 100, or 0 to 10, of 100x plus x cubed minus 20x squared dx, which is a piece of cake. The integral will be 50x squared plus x cubed x to the power 4 by 4 minus 20x cubed by 3. And all of this needs to be evaluated from 0 to 10. So because each term has an x, so whenever you plug in 0, it's going to be 0 anyways. So this will be k times when you plug in 10, you have 50 times 10 squared, which is going to be 100, plus 10 to the power 4 divided by 4 minus 20 times 1,000 divided by 3. Okay, and you might see this is like a gigantic number, but you remember k is a very tiny number. So when you plug in the value of k being 3 divided by 10 to the power of 3 times, it's going to be 5,000 plus by 4, 20,000 by 3. This is the expected value of this whole system. If I was to quickly run this down here and compute it in a calculator, $5,000 plus 10,000 divided by 4 minus 20,000 divided by 3. So see, the average is coming out to be 2.5 units, right? And that's reasonable because the fish will probably weigh, you know, around that number, or else it will just be, you know, a very weird lake, or, you know, plot for some sci-fi movie in that sense, right? So how do you feel about part C now, after we're done this work? How would you, you know, now feel like much easier, right? It's just like one single formula, and interpretation is very important too. Once we can interpret it, then doing the integral is just another piece of cake. Not that bad at all. This wraps up everything about probability that you need to know as a part of this course. Okay, and there are some other things too, which variance and standard deviation. Formula for variance is very straightforward again. As I said, they will probably ask you to find variance of a data. And that is going to be, again, now that we've developed the context of what the whole integrals are and what we're working with, you would just need this. From a to b of x squared f of x minus the expected value of x whole square. So let's see. Finding variance is the hardest because then you would have to do two integrals first of all, right? To get this itself is an integral from a to b of f of x, right? So expected value is already a function that you have to integrate and find the value from, and then you would have to do another integral here too, with now instead of x being an x squared being multiplied with the f of x. Once you get those two quantities, you just subtract that quantity with the expected values square, and you get the result. Okay? Sometimes what we do is, if we go back, the expected value, okay, is also denoted by a symbol called mu. Okay? They also sometimes use this symbol called mu to represent the mean or the expected value or the average. So another way to write that formula in a notational way will be a to b dx minus mu squared. So this is an integral by itself, and then you just subtract the mu squared from it. Or if you want to be a little bit fancy, what I can do is you can be like, this is a to b of the function, where you'll be like, okay, I can try to change this a little bit, and write another formula for. I think they never talked about it, so we'll just stick to this function. Or if you want to be fancy, I'll just do it. That's also equivalent, okay, of having the same formula. So all in all, to find variance, you need to find mu first, and to find mu is already an integral. So variance is like very hard. Computationally, it's not hard necessarily. You know, like an integral will be much easier, but computationally finding variance is very hard. So that's why likelihood of that being showing up on the exam is very low. Okay, that's why they never really go to variance. Most of the time, they only stick to the expected value, PDF, CDFs, and that's it. Okay, but now you have a variance. That's something there. Now what you have another thing is called standard deviation. Which will be the square root of variance of x. So once you find the variance, then you can take the square root of that to get to the final result. Okay. So now I'm going to show you how to computationally find all of these three things. Okay. On Desmos. If you just in case if you want to check your results, or you may be practicing on some things, you might want to do it. So I want to define my PDF here. Okay. This function is f of x, which we found out to be k times 10 minus x whole squared. Okay, and then of course it's asking for the value of k, so I'm going to have to define the k context here. We found out that k needs to be 3 divided by 10 to the power of 3. Okay, and this is how our PDF looks like. It's very weird, but because this is like the whole graph and we're not working on it, we're going to be working on only the portion from 0 to 10. So I'm going to rewrite this, and the only thing you'll see on the graph now is the portion from 0 to 10. So 0 to 10. Of f of x. That way will make more sense. This is how the probability is distributed amongst this zone, right? Okay, where x represents what weight of the fish you might expect, right, to find, and the y value represents the likelihood of finding that. Okay, so in this context, you see the highest likelihood to find is a fish of 0 weight, as per this description, right? Because that's the peak. There's 30% accumulation in that sense, right? So this is the setup that's given to us. Now I'm going to try to just reiterate the formulas there. Okay, the formulas that they were asking for the first part was the value of k. We already did that. That's this one. So I'm going to drag it down so that it looks like coherent. That's the part A. Part B was asking for the probability for it being bigger than 5, right? And you know that's going to be found out by taking the integral from 5 till 10 of the function. And that's 0.125, which we found out to be pretty much the same in our problem as well. Okay, if we go back when we found out the value, it was 5 cubed by 10 cubed. I'll show you what that is. That's exactly the same number. Okay, it just looks different, pretty much the same number. So that validates our part A and part B are correct the way we solved it. So no problem there. The part C, as I said, the expected value, I'm going to call this capital E. This should be equals to integral from 0 to 10, as we said, of x times f of x, right? So when I find that, well, the expected value is 2.5. This is precisely what we got to. So now we had the expected value is E. If you were to find the variance, I'm going to call that capital V. As per the formula, that will be the integral from, of course, 0 to 10 of x squared times f of x. And then you want to subtract. I'm going to put this into like one form. And then subtract the value that you found for E squared. Okay, so the variance for this particular expression came out to be 3.75. Okay, and then if you want to be very careful and want to find standard deviation, I'm going to call that capital S. That's just going to be square root of capital V, which is 1.93419. So this is how you find out everything regarding this particular question. And this kind of quantifies pretty much all the stuff you need. You know, you have to verify and find the value of k to make it a PDF. That's very important. You need to know how to find probabilities. That was covered in part B. You need to know how to find expected value or average value of any quantity. That also was covered in part C. And then, of course, variance and standard deviation becomes too handy, you know, like too hard to do it with a regular calculator, without calculators and anything. That's why they never ask you that, but this is how you do it, and you know you have the values there too. Any questions regarding the whole the whole flow of the topic? Makes sense, right? Yeah. I'm glad. It just kind of like fell into place, so that's good. So now when you have this information and you go and look back at the assignments or anything that you see and encounter, you should be able to very easily go through all of them. Very straightforward stuff, right? Nothing special. And if you, of course, are not able to, I'm always here to help you out with that. No questions there. So now, before we end up, like, we're just going to take 5 minutes more of your time to kind of go over one of the questions Maria was talking about. It was the repeated decimal. So why don't you type in that number for me, Maria, and we'll go over that. Okay, it is a question from Bobrick 10, and the last question. So I'm gonna work on her numbers. Okay, so the question was 9.765, 765, 765. Always repeating, which could be written as 9.765 with a bar. Okay, the key thing to break it down is like this. So you have 9 plus that's the first breakdown you can do. It's 9 plus something, right? And then you can do a further breakdown, be like, okay, this is just gonna be right? I can do those portions and break them down like this. Okay, makes sense? The first breakdown kind of makes sense. That I wrote this first 765 as 765 divided by 1,000, and then plus the remaining all that stuff. And then I'm gonna have one more breakdown to show you how I can write like this. So to write this, I would have 765 divided by 1, 2, 3, 4, 5, 6. Okay, and then the next one we broke it down to 765. Then 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So that's what's gonna happen eventually as you go till the end. Every time you'll have this ratio being multiplied, right? So I'm gonna do some factoring. I'm gonna take 765 over 1,000 out of this. I'll be left with 1 plus 1 over 1,000 plus 1 over 6 zeros, right? Goes all the way. Right? So now what you see here is a geometric series. Right? Where the first term, A, is 1. Because you see the next consecutive term is just being multiplied by 1 over 1,000. So ratio is 1 over 1,000. Right? And then because it never ends, so it's an infinite sequence, infinite series, right? In that sense. So to find the sum of these infinite series, you have a formula. Sum is equals to A over 1 minus R. So in this case, it will just be 1 over 1 minus 1 over 1,000. Okay? So now, I'm going to take all this here. This expression becomes 9 plus 765 over 1,000. And all that sum inside is condensed to 1 over 1 minus 1 over 1,000. And then it's just algebra. plus 765. 1000. If you reduce the inside, you'll get 99 minus 1000 minus 1, so 999 over 1000 on top. This and that cancels out, so you have 9 plus 765 over 999, which could be written as 9 times 999 plus 765 divided by 999. And this is what you will submit as your P, and this is what you submit as your Q. Okay, of course they want you to simplify, so make sure you run it through a calculator, get the exact number, and that's how you will be able to figure it out. Okay, if I was to tell you what it is, it will be 9 times 999 plus 765, all of this divided by, and you see the number is 9.765. 765 is repeating. In the fraction, it should be like this: 1084 divided by 111, and that is your answer for P is 1084, and 111 is the answer for Q. All the pieces fall into place, making sense? Awesome. That's how you do the last question on that problem. And yeah, that concludes our session for today. A little bit longer on probability because we never had like a chance to go over each of the questions before. But yeah, so I kind of explained probability in the beginning and then went over all the kind of questions you can have. Now's the time where you have the opportunity to try them out. And let me know if you have any troubles with any of the questions, right? Yeah, so like I would definitely go like 20 minutes longer and cover up all the essential things rather than just leaving them up to you and then making these sessions not that effective. So my idea was that, of course, at any point if you have any other priorities, you can leave. We have the recording there too, but since you guys are sticking around, might as well just get it going. So yeah, other than that, if you have any questions, please feel free to ask me, or you guys are good to leave and enjoy the rest of your day. I'll be sending the recording for Tuesday because my computer was bugging. So I'm going to send the Tuesdays and Thursdays, both of them will upload right now, and then we'll send it over to you. And as you as well, enjoy your weekend and just relax, a little bit before the finals are going to hit you. That will be my recommendations. Enjoy, guys.
I think I got lost on the very last step of the web work question.
Right here. Let's go. Which one? So I'm gonna mark this was okay. This was okay, right?
Yes.
This was okay as well.
It was like right below that.
So,
how does it
right here
turn into 9.999? Oh, it's 9 times 999.
Yeah, 9 times.
Oh,
999.
totally. Yeah. Okay, totally. Never mind. Yeah, that totally makes sense.
That's 9 times 999 and plus 765 over 999.
Oh yeah.
Right.
Yeah, totally makes sense. Okay,
awesome.
Perfect. Yeah.
No problem. I'm just gonna stop.
Happy long weekend.